Welcome back to chapter 21. This chapter is the last chapter of this particular unit, so we'll have a test coming up at the end of it. And this is also going to finish up our proportion part of confidence intervals and hypothesis tests. We've seen one sample proportion or one sample intervals for proportion, one proportion tests. Now we're going to be looking at what happens if we want to compare two different proportions. What's nice is we'll see that the steps are the same, the conditions and stuff are largely the same. What's different is just the tests that we use. The interpretation will be the same. So let's take a look. So when we're comparing two proportions, a lot of times we want to compare as opposed to just see if one is bigger than or less than something else. And so this lets us compare two things like the two groups with a treatment or a placebo, or this year and last year. Things like that. We can compare two different populations. We could compare the state of Washington, the state of California with something. And so that comparison is a powerful and useful thing that we do fairly frequently. So when we're examining the difference between two proportions or anything else, we always have to have the standard deviation. Well, remember, standard deviations don't add, but the variances do. So when we are subtracting or adding two random variables, we always add the variances. So we could take the standard deviations, square them, add them together, and then square root to find the standard deviation of a difference, which is going to come in handy very, very soon. And this is not something you're generally going to be finding, by the way. These tests are getting a little bit more complicated. Like the equations get kind of ugly. As you can see, the standard deviation equation's kind of ugly. Use your calculator or StatCrunch or something. Generally speaking, don't be doing these tests and stuff by hand. I know that sounds weird to hear from your teacher, but don't do it by hand. So we saw the standard deviation of differences. We square the standard deviation, add them together, then square root. Well, remember the standard deviation of a proportion was the square root of p times q over n. So when we square that, we get these guys, the p times q over n, and then we square root. And notice we have the one for the first sample plus the one for the second sample. And then the standard error, same thing, except we use p hat and q hat because the standard error is based off of the sample that we got, because we don't always know the population proportion. In fact, we don't generally know the population proportion. Oh, that's what I was. So remember that P is the probability of success. Q is the probability of failure, which would be 1 minus P. So some assumptions. First, the independent assumptions. We have to have independent groups. They must be independent of each other. So the different types of groups, we could have 2 different years. We could have people or something in 2 different states or 2 different areas. We could have 2 different ages or grade levels. We want to compare the juniors and the seniors. That's okay. We could have two different genders, want to compare men and women. Um, so the two groups have to be independent of each other. The samples that we take from them have to be independent as well. We need simple random samples from each group. For instance, if we were to compare um, the political leanings or something of men and women, and to see if they're different. If we found a whole bunch of married couples and asked the husband and the wife, those would not be two independent samples. We would have to get like all the men in the whatever the region is we're looking for, select a sample randomly from them. Then do the same thing with all the women. Is it possible that we might get a couple pairings? Yes, that's possible, but that's just the random sampling. Um, you need to take the sample independently for each population. Um, and that's what that says. So the randomization, they need to be drawn randomly at 10%. We can't have people with, or we can't get more than 10% of the population because that starts changing the probability. So same thing as before. The size, each group has to be big enough. Both groups need at least 10 successes and at least 10 failures. I've seen some textbooks say instead of 10 for the two sample, 5 is big enough. Has to be at least 5 for each of them. The AP test doesn't matter. You could use either. Generally speaking, they're going to be bigger than 10 anyway, so it doesn't really make much of a difference. But I've seen 10, I've seen 5. Statistics, we can't even agree on some of this basic stuff. But again, the AP test accepts either. So if you were doing the AP test and you said that, oh, and these are both greater than 5, they would accept that as a condition. If you said, oh, these are both greater than 10, they would accept that as a condition. So, does not matter. So now for a confidence interval. So we know that we have large enough samples. If each of our samples is going to be approximately normal. And so if we subtract them, that will also be approximately normal, because when we add or subtract normal distributions, we end up with another normal distribution. So, assuming all the conditions are met, we're looking for the sampling distribution of P1 hat minus P2 hat. We're looking at the sampling distribution of the difference. The mean is going to be P1 minus P2. We don't generally know those. The standard deviation of P1 hat minus P2 hat is going to be that the sum of the standard deviations or the sum of the variances then square rooted. And so to get our confidence interval, it's the mean, right? Remember, our confidence interval is always, or it was P hat plus or minus Z star times the standard error of P hat. Same thing. It's our mean, the center, which in this case is P1 hat minus P2 hat, plus or minus Z star times the standard error of P1 hat minus P2 hat. Z star is still what we want for our confidence level. The values are the same. We can find them from the Z table, or that bottom row of the T table gives us the confidence intervals. And it's interpreted the same. Now, as you can see, that equation is not particularly a pleasant one to write, especially if you were to put this in place of the standard error of p1 hat minus p2 hat. Remember, when you're doing things, and say for the AP test, you need to define what test you're using by formula or by name. Personally, hey, I need to do a 2 proportion z interval. I'm going to write down that, not this, just because it's a lot easier. Also, remember a couple slides ago, I told you don't do this by hand. Use your calculator. It's because of stuff like this. Um, so, um, so for a hypothesis test, and so the confidence interval, again, we were estimating the mean of that difference. Hypothesis test, we're going to test a hypothesis against an alternative. So the typical hypothesis test for a difference is going to have one of two hypotheses. It can either be this one here, that h naught equals p1, or h naught is p1 minus p2 equals 0. When we subtract them, we get 0. Or we could also say h naught p1 equals p2. Notice that these two things were equivalent statements. If we added the p2 over, it would be the same. Also notice it's p1 and p2. We don't have hats on these. And the 1 and the 2 don't have to be 1 and 2, by the way. If you have a problem where something other than 1 and 2 makes sense, for instance, let's say you're testing a drug and a placebo. We could have P of D and P of P for placebo. So you can have it be whatever you want. If it's not obvious, make sure that you label it. So, continuing on, since we're hypothesizing that there's no actual difference between the two proportions, that means that the standard deviations for each of them will be the same. Because remember, the standard deviation for a proportion is going to be the square root of p minus q over n. Well, if we're subtracting, or if the p's are the same, then the standard deviations will be the same, because it's based off of the standard deviation. And this also is if n is close to the same amount too, it works a lot better. Anyway, when this is the case, we can pool the standard deviations, and we're going to talk about pooling, and this particular book says that it's very important. Other books say that it's not particularly important. The AP test doesn't particularly care one way or the other. When you are finding these things in your calculator, one of the options will be pooled, yes or no. Because you're not going to be finding them by hand. Well, you could find them by hand. I would not recommend finding these by hand. Use your calculator. You can select the pooled option. You cannot select the pooled option. But we're going to see more about what the pooled option is here. So, we want to get a pooled proportion. So the p hat for pooled, we just add them. How many successes total divided by how many total trials. So if we had, say, 20 out of 100 and 30 out of 120, the pooled would be 20 plus 30 is 50 out of 220. Notice that is not just the two proportions added together, right? Because we would have to find common denominators. This is how you always really wanted to add fractions. Just add the tops, add the bottoms. You get your pooled proportion. Um, so the success, that's just n times p1. It's how many successes it would be. Um, so, and then if they're not whole numbers, round them first, which is kind of weird because you don't usually round in the middle of a problem, but that's okay. So we went n times p in the first one, we got 19.6. All right, so that's 20 over the 100. And then the same thing with the other one. For the standard error, we would do the same. We have p hat pooled, q hat pooled, so we do the pooled ones for each of them. And then standard error formula. Notice that this is almost 2 times that, except that we have n1 and n2. Again, you're not actually going to be using this formula, generally speaking. Your calculator is going to do it for you. This is just what the pooled formula is. So what do we compare it to? So reject the null hypothesis if we see a large enough difference in the two proportions, right? The same as we would normally. How can we decide if it's large? Compare it with the standard deviation, right? If it's more than 2 standard deviations away from the mean, it's typically large. So this is the same stuff we do. We find that z star. However, being that the null hypothesis equals 0, it doesn't really give us a standard deviation because we'd have 0 times something over n plus 0 times something over n, then we square root. We have 0, so that doesn't work. So instead of using the standard deviation, we just use the standard error, which we found on the last page, and it's pooled. Again, you're not going to be finding these. Generally, the calculator is going to do all that. You're not even going to see it happen. That's all part of the mechanics. And so, the two proportion z-test, the conditions, same as the z-interval, we have to have independent populations, independent samples, random, have to have at least 10 or 5 successes and failures for both samples, and no more than 10% of the population for each of them. And we're testing the hypotheses. H naught is P1 minus P2 equals 0, or H naught is P1 equals P2. The alternative hypotheses, greater than, less than, or not equal to. A lot of times, this one's a little bit easier to write the alternative hypothesis because this one you have to be thinking about, is it going to be positive or negative? Like if I think P2 is going to be smaller, that means that it would be a positive value, so it'd be greater than 0. If P2 is bigger, it would be a negative value, so it'd be less than 0. And so it's just a little bit more to think about. So we can pool the proportions. We can use the pooled value to estimate that standard error. Find the test statistic. So this is our z-score. It's the p hat 1 minus p hat 2 minus 0 because this is that null hypothesis over the standard error of p1 hat minus p2 hat. The z-score is the same z-score we had already. We would take it to table A, we would find the p-value, and we would interpret that against an alpha level. Because when the conditions are met, it should be normal, so we get the p-value. Again, when we're doing the test or something, one of the things we have to do is we have to name the test that we're doing by either the formula or the name. This formula is kind of ugly. hey, we're going to do a two proportion z-test. That's what we're doing. You don't need to write down the formula. We're doing a two proportion z-test. Here's my p1 hat, p2 hat, n1, n2, z equals this, p equals this, and then you can get into the meaning. Is it significant or not? Remember that running the test is part of the work. The answer is it significant or not, and in context. You don't have to show these steps. Your calculator can do it for you. In fact, unlike on things like the AP test, it's expected that your calculator is going to do it for you. It's not the actual doing it. It's, are you doing the right thing? Does it meet the conditions? Can you do it? And then what does it mean? Those are the things that they're looking for. So what can go wrong when we're doing these? Don't use the two sample methods if they're not independent. That does not work. We've talked about matched pairs a little bit. We'll talk about matched pairs more. Those are not two independent samples. That would be a one sample test. Don't apply the inference methods when there's no randomization. The randomness is very important. And don't interpret a significant difference in proportions causally. I always want to read that as casually, but it's causally. We're showing there is a difference in proportions. We're not showing cause and effect here. It's like, hey, there's a difference in proportions. And then that could lead other people to determine whether or not there's a cause and effect relationship. But remember, just because there's a correlation doesn't imply causation. Same thing, if there's a difference in proportions, that does not mean that one thing causes the other. There could be a lot of other things. So what have we learned? We've gone from one sample proportion tests and intervals to two sample proportion tests and intervals. They're basically the same, except you would use a different test um, in your calculator, or a different interval in your calculator. Also, the two populations have to be independent. And so that's a big one that we see. I love the Pythagorean theorem of statistics. That's when we're adding the two variances together and square rooting to get the standard deviation. I love they call it that. Um, Learn that when the null hypotheses assume the proportions are equal, we can, not necessarily must, we can pool the samples to estimate the true proportion. In confidence intervals, we don't, because we're not assuming that they're equal. We're looking for what would the difference be. And again, I've mentioned this, most important, we've learned that the concepts, reasoning, interpretations of statistical inference remain the same, only the mechanics change. It's that step 3 on how to run the actual test. You name the test. Again, use your calculator. You're just using a different test than the one sample ones. AP tips. Check your conditions. The two independent groups is an important new condition. When stating your conclusion, make clear that you're talking about the difference of the two proportions. And the formulas are complicated. If you write them on an assessment, make sure that they are right. Make sure that you copy them down. Better yet, don't write them on the assessment. Use the name. Two proportion Z interval. Two proportion Z test. I would use those. So this is it for chapter 21. I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.